In this video, we'll discuss the relation of quantum pumps to modern theory of polarization density and Wannier representation. And this is Wannier. So let's start. So the polarization density. By definition, the polarization density obeys this equation. The divergence of the polarization density is equal to minus rho. Rho is simply the density. Using also the continuity equation, we know that the rho to dt plus divergence of j is equal to 0. Now we can substitute the first equation in the second one. So we immediately get that the p to dt minus j is equal to 0. Integrate that out, we find up to the divergence-free part. What we find is that a change in the polarization density, is given, I emphasize that this is the change, is given by the integral from 0 up to t in jt dt. So if we have current in the system, it causes a change in the polarization density. Now, as usual, we want to treat the system in terms of the adiabatic evolution. So instead of thinking about time evolution, we think about change of parameters that depend on time. So t goes to lambda t. And I would like to set at t equal to 0, lambda is equal to 0. So for example, if we start from u equal to 0 in the Rice-Meili model, we will multiply it by lambda, and lambda is equal to 0 initially, and at time t, which is equal to a capital time t, we set lambda equal to 1. The formulas that we found for the current in terms of the Berry curvature can be applied here in a more general form. Earlier, we discussed only the one-dimensional situation, and this is the generalization to d dimensions. D could be either 1, 2, or 3. Or even more if you think about more abstract. In 1D, this formula, we already met it in this course. Delta p is equal to minus e, the integral from 0 to 1 d lambda, the integral of dk from minus pi to pi of the Berry curvature. And that, in turn, is given by the integral of the Berry connection. Now, A is given by AL. The components of AL are U times D to the L, U, where in this case, L is equal to lambda or K. And this is simply, remind us, the Berry phase. The first one to introduce this discussion in solid was Zach. This is why we call that phase the Zach's phase. So here is Joshua Zach. So now we want to generalize that result to 3 dimensions. So delta p of L will be equal to minus e, the integral dk x dk y times the integral dk z. And here we'll have b of L k x, k y, k z, and lambda. And we, of course, have to integrate over lambda as well. The integral from 0 to 1 d lambda. So these two integrals together form a Zach phase, which depends on the component L of the Berry curvature. In this case, we integrate on kz, so it will depend on kx and ky. And we integrate on kz and lambda, so this is the phase that we get. So this is, usually we give the symbol z for the Zach phase. So in every polarization, change in the polarization density, we will have a relation to the Zach phase. So let's continue. We would like to relate these formulas to the Wannier function. So I remind you what we got so far. So with this equation, bj k lambda is equal to d kj a lambda minus d lambda akj. This is the standard relation between the Berry curvature and the Berry connection. And due to the periodic boundary condition of A with respect to K, remember we discussed a lattice in 3 dimensions, we can always choose a gauge such that the integral on the Brillouin zone of dk, dkl, d lambda, k lambda is equal to 0. And then we get the following result. So delta PL is equal to E times the integral on the Brillouin zone, AKL, is calculated at lambda equal to 0 and lambda equal to 1. This is the change in the polarization operator in the direction L. So let me remind you what are these AKL. They are related by definition to the derivative of the wave functions themselves. Now when you think about it, this is very surprising. Delta PL is polarization density. It was related somehow to the charge. But in the calculation that we find here, due to this adiabatic transfers and so on, the change in the polarization, not only about the density, but also on the phases of the wave functions. And this is a very important observation, which is not intuitive. The polarization density depends on the phases of the wave functions, which contain a lot of information about the topology of the system and so on. We also have to define A lambda, and of course L is equal to X, Y, and Z. We also have to define A lambda of K and lambda, which is given by that equation. So this is a relation between the polarization operator and the Berry connections, and we have in mind that in the background we have also the ZAC. So now I would like to discuss the change in the polarization density and the Wannier functions. What is the relation between them? So I remind you things that we all should know. The relation between the Bloch function and the periodic Bloch function and the Wannier function. So here, these are the Bloch functions, which are related to the n here is the band index. The u are periodic function, with r being the Bravais lattice vectors, and w is the local Wannier function. So in deriving the relation in Fourier space between the Wannier functions and the Bloch function, one has to be very careful about the choice of the normalization factor. So here is a consistent choice of normalization factor. Here the choice of V is such that this is the volume of a unit cell. So what we would like to do now, is to show you pictorially what is the relation between psi, u, and w. So the point is that we can think about the Wannier functions as some kind of a wave packet. So this is the expression for the Bloch function, which is plotted here as a function of space. The envelope is simply e to the ikx, and the oscillations, the yellow part, is the Bloch function. This is related to the periodic function u in the following way, and pictorially this will behave like that. So you see that now we have a periodic function without the envelope. So u of r is equal to u of r plus r. So this is the periodic function uk of x, and the Wannier function is, this is equal to the Wannier function, is local in space, so it has this envelope around the atom. So we can think about it as wave packets describing this atom. So just remember that these are the relations between the Bloch function and the Wannier function. So now we remember that we have the relation between delta P L, and A was related to some derivatives of these operators, these wave functions u. Using, this is written here. So now using this relation and the relation between the Wannier function and this periodic u function, one can simply derive the following result. Delta PL is equal to E times the integral with this factor r. R is appeared there because we have here derivative with respect to k of the difference in the Wannier functions at lambda equal to 1 and lambda equal to 0. So this is we find the relation between the change in the polarization operator and the center of mass of the Wannier function. the change in the polarization density is given by the integrals of R times the difference between the Wannier functions. This formula here is known as the King-Smith and Vanderbilt formula. Now what I want you to pay attention is that we actually have a physical interpretation of this formula. The change in the polarization density is given by the change in the center of mass of the Wannier functions. So if we have at lambda equal to 0 this Wannier function, and as we change the lambda from 0 to 1, the center of mass of the Wannier function move in this direction. This will be the lambda equal to 1. The difference between the two give us the change in the polarization density. I would like to finish this video by saying that this King-Smith-Vanderbilt formula includes the integer part of the pumping as well as the Zach phase.